Conservation of energy is something we keep coming back to over and over in physics, and that's because it's one of the fundamental properties of the universe. Energy is always conserved. Now that we've introduced a new kind of potential energy, the electric potential energy, let's see how that fits in with our equation for conservation of energy. So conservation of energy states that our final energy is equal to our initial energy, plus any work done by non-conservative forces. This is work done by things like friction and air resistance. We're going to assume that this whole part is about zero. So we're going to talk about cases where energy is exactly the same initially and finally because we don't have things like friction. So the kinds of energy we can have are kinetic and potential. Our kinds of potential energy we can have are gravitational, spring. We've talked about those so far this course. And now we've also got electric. And we, in general, will include all of the kinds of energy when we write our equations. So our kinetic energy is 1/2 mv squared. That's the energy associated with something that's moving. Gravitational potential energy, that's mgh. It's the energy that mass has when it's up at a height h in the air. When we're doing problems with protons and electrons, I'm going to say that m is usually, I'll stress the word usually because not always, but usually m is small. If m is small, and then I'll put in brackets protons and electrons. If m is small, then we can say that our gravitational potential energy is pretty close to zero and we can neglect it. It's so tiny it doesn't make any difference. Our spring potential energy is equal to 1/2 times k times x squared. We did that what feels like a million years ago. In these problems with moving charges in electric fields, there are no springs. That tells us for these problems that we're working on now, our spring potential energy is going to be zero because we don't have a spring. The last thing we'll layer in is that our electric potential energy is equal to the charge times the potential V. So overall, that's going to boil down to our gravitational potential energy is about zero, our spring potential energy is zero, gravitational is about zero, spring is zero. That leaves us with an equation that says K final plus charge times potential final, that's our final electric potential energy, equals K initial plus Q times V initial. We're often given change in potential. That means VF minus VI. And in cases like that, it's okay to assume, and we often do assume, that VI equals zero. It's like you're putting your origin at that initial spot. That's what that means when you think about it. That's where you put that S value equals zero. So this is our expression for conservation of energy when we include electric potential energy. Next, we'll move on to doing some conservation of energy problems for charges that move around in electric fields. In our example now, we have a capacitor charged to a potential difference of 12 volts. So delta V equals 12 volts. The distance between the plates is 2 millimeters. And the electric field between the plates is 6,000 newtons per coulomb. We can see from our picture that that field points to the right, so that we can say E equals 6,000 newtons per coulomb in the x direction. What else will we put here? We know that electric field goes from positive to negative or from high potential to low potential. Let's label this side as high. Let's label this side as low. A proton is released from rest at the positive plate. So we take a proton and we're going to let it go right here. There's a little positive charge. Okay, part A. Which way does the proton move and why? So I would suggest you hit pause and answer this question for yourself, or maybe you don't even need to hit pause. So which way does the proton move? The proton is going to move towards the right. That tends to be the easier part of the question to answer. The hardest part is why does it move to the right? There are different ways to explain this answer. Okay, one possible way you could answer it is you could say that it moves towards lower potential energy. And we know which side has the low potential energy because potential energy is charge times potential. And objects always move under their own steam towards low potential energy. You could also say that it moves towards lower potential because we know that's what positive charges do. Oops, I left out the word low. Put that back in. And if you prefer to think about forces, it will be pushed by the force. Force on it is the electric force, which is charge times the electric field. So the electric force pushes it to the right, so it would move to the right. So if you had this question, you could explain it in any of those three ways. Okay, so it starts here, it's going to move along, it's going to keep going with that force. Because there's a force on it, we kind of anticipate that it's going to keep speeding up, and eventually it's going to come over and bang into the negative plate. Find the speed of the proton as it reaches the negative plate. Now, you do have two strategies to solve this problem. I'll talk you through the first strategy, and you can work on it if you wish. You can find the force, and you know force equals mass times acceleration, so you could find the acceleration. Then you know the distance between the plates, so you could use one of your kinematics equations to find the speed as it got to the negative plate. Your initial speed would be 0. That's perfectly legitimate, but since we're doing the section on energy, let's solve this problem using conservation of energy. Because there's no friction or anything like that going on, we're going to say that our final energy equals our initial energy. Our final energy is going to be our final kinetic plus our final electric potential. We don't have any gravitational potential or any spring potential. That's going to be equal to our initial energy, which is K initial, plus electric initial potential energy. Okay, now let's remember that kinetic energy equals 1/2 times m times velocity squared, and electric potential energy is charge times potential. Let's fill those bits in. Okay, so far so good. Is there anything that we have here that's 0 that we can cancel out? Well, we know that our initial speed is 0 because the proton was released from rest. So this whole bit can go. Let's write our equation out once more. I'm trying to be careful with my V's here. My speed is a lowercase cursive V. My potentials are an uppercase handwritten V, printed V. Okay, what else can we do here? Q means the charge of the proton. And the charge on the proton is equal to positive of the fundamental charge plus 1.6 times 10 to the minus 19. I'll fill that guy in too. Okay, so we're trying to solve for our final velocity. So let's keep going with the algebra and let's find our final velocity. This slide is after getting a bit full, so we'll go on to the next blank one. Let's keep going with our algebra now. Remember, we're trying to solve for our final speed. So 1/2 times m times vf squared equals the charge times vi minus the charge times vf. I can take my charge outside, vi minus vf. What else do we have here now? So now I would like to solve for my vf. I'll divide both sides by 1/2 m. Okay, looks like I'm ready to put some numbers in here now. Oh wait, I suppose I should take the square root first, shouldn't I? So VF is going to be the square root of all this business. Okay, so let's get a list of what numbers we have to plug in. E is our fundamental charge, 1.6 times 10 to the minus 19 coulombs. M is the mass of the proton. You probably don't remember that off the top of your head. Sadly, I do. But you can certainly look it up on Google or in your book. Okay, the last one is a little tiny bit tricky. It's your VI minus VF. We know the change in potential is 12 volts, but are we going to put in plus 12 volts or minus 12 volts? Sometimes it's going to be minus, sometimes it's going to be plus. Let's see what we know. We know that delta V equals 12 volts. So that tells us that the difference in potential between the two plates is 12. We'll need to look at our picture and see which one is bigger and which one is smaller. So our high potential is over at our initial point. Our low potential is over at our final point. So delta V is 12 volts. So VI minus VF. VI is a high number. This is a big number. Take away VF. This is a small number. So a big number take away a small number is going to give us a positive number. So VI minus VF equals 12 volts. As we go from the start to the finish, our potential gets smaller. So VI minus VF is plus 12 volts. Okay, you've always got to be really careful about that part because it can be easy to get a wonky negative sign put in. Let's put our numbers in. 1.6 times 10 to the minus 19 coulombs times VI minus VF, which is 12 volts, divided by 1/2 times M, which is 1.67 times 10 to the minus 27 kilograms. Put all that through the calculator, and what we get is 1.52 times 10 to the 8 meters per second. It's pretty fast, but then it is a little tiny particle, so that's whizzing through there. It's smaller than the speed of light, so we're still safe. The place you have to be careful for here is your negative signs under your square roots. If you get a negative sign under the square root, it shows you that you've made a mistake and you need to go back and you need to troubleshoot it and see where you went wrong. Most likely it came from finding those two potentials. Yeah. Okay, so what the other approach you could take is, over at your final spot, that's at the negative plate. Normally we say that's a potential of 0. And then at your high spot, we know that it has to be different by 12 volts and it has to be higher. So your initial V could be plus 12. So that would be another way to do it as well. So over here at your final spot, that's where your position equals 0 because you're right on top of the plate. So your potential is equal to 0. At your high spot, at your initial point, we know that delta V equals 12 volts. So V initial equals plus 12 volts. So that's a different way to look at it. There's lots of different ways. Whichever makes most sense to you is probably the way you should stick with. Let's do a problem now that's just a little bit different. We have our same capacitor. It's charged to a potential difference of 12 volts spaced by 2 millimeters, and the field is 6,000 newtons per coulomb. This time we're going to project an electron from the positive plate with a speed of 1.75 times 10 to the 6 meters per second. That means we're going to start our electron at the negative plate, and we're going to give it some sort of an initial velocity. Then we're asking what happens to it after that. So let's get some ideas put down on our picture. We know our electric field is 6,000 newtons per coulomb. We know electric field points from high potential to low potential. So our positive plate is the one with high potential. Our negative plate is the one with low potential. If we pick our value of S at our negative plate, then we know that our negative plate would have a potential of 0. Our positive plate, we know the difference between the two of them is 12 volts, and the positive plate is 12 volts higher than the negative plate. So our positive plate would have a potential of 12 volts. Okay, so that's our setup. And we know that the initial velocity is 1.75 times 10 to the 6 meters per second. There's our initial velocity. Now let's ask what happens to the electron. So what is the motion? The initial velocity is to the right. What about the electric force? The electric force is the charge on the electron times the electric field. The charge on the electron is minus E. So the electric force is to the left. If the force is to the left, then the acceleration, which is force over mass, is also to the left. So if we throw something to the right, but it has an acceleration to the left, the motion is that it's going to slow down, it's going to turn, and then it's going to move left. Okay, kind of like how things work when you throw them up in the air. So you throw it up, it slows down, slows down, slows down till it gets to the top, then it turns around, it comes back. Same deal happens here, except for it's moving to the right, and then it stops and turns around and comes back. So let's look at what question A is asking us. Question A says, does the electron reach the negative plate? So how are we going to figure that part out? Does it reach? So what we know is that at the turning point, VF equals 0. So what we could do is we could figure out some information about what do we know when VF equals 0. If we can find more or less where the turning point is, then we'll know if it reaches or not. If our turning point is before we hit the plate, then no, it can't reach. If it's after we hit the plate, then yes, it does reach. So from conservation of energy, we know that if we know speed, we can figure out potential. So let's ask, what is V, the potential, when our final velocity equals 0? If VF is between 12 and 0, it doesn't reach. So then the path would look something like this. It would get projected to the right and it would turn around and come back beforehand. So this would have a positive potential right here. If V is equal to 0, then it exactly reaches, or just barely reaches. So let's draw what that situation would look like. It would get there and come back. And then if it overshoots, so that's one option, that's two options, and then three options. If our final potential kind of went past 0, it got to negative, then it would overshoot. Then the practical impact is it would smack into it with some velocity. So if our final potential is bigger, it means kind of if that plate wasn't in the way, it would go past and come back. So we're trying to figure out which one is our best match right here. So let's apply our conservation of energy. Let's figure out the potential when the V is equal to 0. Let's think about what that means and we'll be able to answer part A. Let's write down our expression for conservation of energy. Final kinetic plus final electric potential equals initial kinetic plus initial electric potential. Remember, we start over here with an initial velocity. That's to the right. V initial was given as 1.75 times 10 to the 6 meters per second. We're asking what is our final potential when our speed equals 0. So let's get in the forms of our equation. 1/2 times m times vf squared plus q times that final potential equals 1/2 times m times v initial squared plus q times that initial potential. Vf is equal to 0 because we're asking what is the potential where it stops.
So Q times VF equals 1/2 times M times VI squared plus Q times VI. I'll divide both sides by Q. Then Q over Q here. So those Q's cancel. Then last, let's remember Q means the charge on the electron, which is minus the fundamental charge, minus 1.6 times 10 to the minus 19 coulombs. M means the mass of the electron, which is 9.11 times 10 to the minus 31 kilograms. What else do we know here? VI is our potential at the initial plate, so this was our initial, this was our final. We know that the negative plate is the low potential, we called that 0 volts. They're different by 12 volts, so our initial potential was 12 volts. Let's put in our numbers here and see what we get for our VF. Whoops, I meant to change colors. So VF is equal to 1/2 times the mass times the speed squared, 1.75 times 10 to the 6 meters per second squared, divided by the charge, which is minus 1.6 times 10 to the minus 19 coulombs, plus our initial potential, which is 12 volts. Put all that through the calculator, and what we should get is 3.28 volts. Now you could even find that position if you wanted to, because we remember that potential is the field times the distance, so we could figure out how far away that is. But it's about right here. So here is where V equals 3.28 volts. So what happens in our motion is that it moves to the right, it slows until it gets to this spot, then it turns around and comes back. So that's what happens here. So now the next part of the question was, how fast, so we should write down our conclusion, shouldn't we? So it doesn't reach V equals 0. Therefore, it doesn't reach negative plate. Yeah, if you were thinking about additional questions I could ask here, you could also be asked to find the distance, right? So that wouldn't be real hard to do, but it would be good to figure out. If you had thought about solving this with kinematics, that would have been absolutely fine. You know the charge and you know the field, so you could find the force. With the force, you could find the acceleration. With the acceleration and your kinematics, you could find the distance to where it stopped. If the distance is less than 2 millimeters, it stops. Bigger than 2 millimeters, it hits. Okay, the next part of the question was, how fast would the electron have to be projected in order to reach the negative plate? So we're going to apply our same process, but this time we're going to have a new set of conditions, which is that it will reach the negative plate, and we'll want to find the new speed. So let's get going with part B. Let's just very quickly put back in the information we have now that we've got a clean slide. So our electron starts right here. For part B, we want it to get all the way over to the other side, and then we know it would turn around and come back. So this is our initial point. This is our final point. We know that our positive plate is the high potential, so our V initial is 12 volts. Our negative plate is the low potential, VF equals 0 volts. Let's write down our equation from that we did in part A, which was that final kinetic plus final potential equals initial kinetic plus initial potential. I'll go through this pretty quickly because we just did this in part A. It's probably boring to listen to it again. 1/2 mVF squared plus Q times VF equals 1/2 times M times VI squared plus Q times VI. Let's see if there are any zeros here. Our VF is 0 because we want it to just reach the negative plate. So that's our final speed. Our final potential is also 0 because we wrote that down. So we know that that's 0. So that tells us that 0 equals 1/2 times M times VI squared plus Q times VI. Got to be careful with your V's here. We're trying to find our initial speed. So 1/2 times M times initial speed squared equals minus Q times initial potential. Got to be super careful with your negative signs here. You don't want to drop any of them. I'm going to solve for my V initial. V initial squared equals minus Q times VI over 1/2 m. If I want to find my speed, then I have to take the square root of both sides. Then I have to be able to put my numbers in. Q means the charge of the electron, which is minus the fundamental charge, minus 1.6 times 10 to the minus 19. My VI is my initial potential, that's 12 volts, and my mass is my electron mass, 9.11 times 10 to the minus 31 kilograms. Again, you have to be so careful with those negative signs. If you have a stray negative inside your square root, it means you made a mistake somewhere. So I've got minus my Q, which is minus 1.6 times 10 to the minus 19 coulombs, times initial potential, 12 volts, divided by 1/2 times my mass. See that inside my square root I have a negative times a negative. That gives me a positive. And my final speed, the speed turns out to be 2.05 times 10 to the 6 meters per second. This is a little bigger than the speed we had in part A, but that's an anticipated result because we want it to go a little further than it did in part A. So if we project it with this speed, it will just get to that negative plate.